The last lecture discussed how to compute magnetic field from a straight source current. This lecture will discuss how to compute magnetic field from a circular current carrying wire. Let's say the current flows clockwise, so from the top view it should look like this. How shall we then visualize the magnetic field produced by this circular source current? Well, we learned Ampere's right-hand rule in the last lecture, didn't we? So we shall call upon the rule again in this lecture. Remember to use your right hand, form the thumbs up sign, and align the thumb along the direction of source current. Depending where we place our thumb along the wire, it will be pointing at different direction at different segments of the wire. But for sure, it should always be pointing in the same direction as the current flow on that segment. Now the curl of our forefingers gives the direction of the magnetic field. So, I want you to visualize grasping an imaginary ring in the way shown in this figure. You should immediately realize that your forefingers are curling into the ring wire. So seen from the top, the magnetic field will also be curling into the wire. It is a little bit hard to visualize what is supposed to be a three-dimensional field on a two-dimensional slide. So allow me to introduce these two symbols. One, a dot. Dot is used to represent the direction of magnetic field if it is pointing to us out of the slide. And two, a cross. Cross is used to represent the magnetic field if it is pointing away from us into the slide. Thus, in this regards, the direction of magnetic field outside the ring is shown by the dots, while the direction of the magnetic field inside the ring is shown by the crosses. From bird's eye point of view, we can thus imagine the magnetic field around the ring current to be as such. Notice how the field lines are curling into the ring from the top. If we reverse the current flows in the wire, that means we have to reverse the direction of the thumb so that the magnetic field, as seen from the top, is curling out of the ring wire as shown by the curling of the forefingers. The direction of the field will be reversed as well. I believe this should not be your first time to see magnetic field lines in this manner. Earth's magnetic field has the same characteristic, so does magnetic field from a bar magnet. But you may be wondering, in such cases, where is the source current? What or where is a source current that generates Earth's magnetic fields, for instance? Well, you can easily find our answer in Wikipedia, though it is still hypothesized. In a bar magnet, the explanation is more complicated. Material is made of atoms. An atom is made of protons, neutrons, and electrons. Now, it turns out that electrons are spinning. Like a current flowing across a ring wire, the spinning of electron, which itself is a charged particle and hence spinning electron can be considered as moving charge, generates magnetic field like a bar magnet, albeit a tiny one. Now imagine many of these spinning electrons come together and align themselves in uniform direction. The resultant effect is the bar magnet. Okay, I should admit that I have oversimplified the explanation. But the message I'm trying to get across is that magnetic field is produced by current or moving charge. A spinning electron is still an instance of moving charge. When a charge moves in circular fashion, we should expect this sort of magnetic field lines. How about the magnitude of the field? Well, the magnitude of the field at the center of the ring is given by this equation, where r refers to the radius of the circular wire. Wait a minute. Are you saying that this equation only holds at the center of the ring current? Indeed it is. What a useful equation. Of all points in space, we can only use it to compute the field at the center of the ring. How about the field at points nearby, such as the field at a point above the ring? Well, we will discuss this in the next lecture. Lastly, what happens if we have many of such ring currents stacked together? Such geometry is called a solenoid, by the way. Well, it should not be too hard to imagine that such current configuration will generate magnetic field in this manner. It's like superimposing field for many single ring currents. Notice that the magnetic field inside a current-carrying solenoid is more or less uniform, except for the field around the two ends of the solenoid. The magnitude of the field can be computed using the following equation. Sometimes like to write the equation in terms of the loop density or coil density of the solenoid. In summary, we have different equations to deal with different current configuration: straight current, loop current, and current in solenoid. At this stage, you may be wondering, in the case of electric field, we have only one equation to compute electric field from different kind of charge configuration. Why do we now have different equations to deal with different current configuration? Or to put it another way, like Coulomb's law, is there a universal equation to compute magnetic field from different current configuration? The answer is yes. and that will be the topic for next lecture.